Now the next topic is intensity transformations. Now we start with introduction. The term spatial domain refers to the image plane itself, and methods in this category are based on direct manipulation of pixels in an image. The spatial domain processes are denoted by the expression g x comma y equals to t of f x comma y, where f x comma y is the input image, g x comma y is the output or processed image, and t is an operator on f defined over a specified neighborhood about point x comma y. Next is intensity transformation functions. So the first intensity transformation function is imadjust. Function imadjust is the basic IPT function for intensity transformations of grayscale images. It has the general syntax as shown below. This function maps the intensity values in image F to new values in G such that values between low in and high in map to values between low out and high out. Values below low in and above high in are clipped, that is, values below low in map to low out and those above high in map to above high out. The input image can be of class unit 8, unit 16, int 16, single or double, and the output image has the same class as the input. All inputs to function imadjust other than f and gamma are specified as values between 0 and 1 independently of the class of f. Parameters gamma specifies the shape of the curve that maps the intensity values in f to create G. If gamma is less than 1, the mapping is weighted toward higher or brighter output values. If gamma is greater than 1, the mapping is weighted toward lower or darker output values. If it is omitted from the function argument, gamma defaults to 1, that is linear mapping. The negative of an image can be obtained with toolbox function imComplement, whose syntax is g equals to imComplement f. Next is logarithmic and contrast stretching transformations. Logarithmic and contrast stretching transformations are basic tools for dynamic range manipulation. Logarithmic transformations are implemented by using the expression g equals to c into log of 1 plus f, where c is a constant and f is floating point. One of the principal uses of log transformation is to compress dynamic range. When performing a log transformation, it is often desirable to bring the resulting compressed values back to the full range of the display. For 8 bits, the easiest way to do this in MATLAB is with this statement, that is gs equals to im to unit 8 mat to gray of g. Using mat to gray brings the values to the range 0 to 1, and using im to unit 8 brings them to the range 0 to 255, converting the image to class unit 8. The function in figure A is called a contrast stretching transformation function because it expands a narrow range of input levels into a wide or stretched range of output levels. The result is an image of higher contrast. In fact, in the limiting case shown in figure B, the output is a binary image. This limiting function is called a thresholding function, which is a simple tool used for image segmentation. Next is handling a variable number of input and or outputs. Function nargn is used to check the number of arguments input into the m function. Function nargout is used in connection with the outputs of an m function. To check if the correct number of arguments were passed in the body of an m function, nargcheck function is used. Next is function to compute negative, gamma, log and contrast stretching. So function change class is basically used for this purpose, whose general syntax is shown below as g equals to change class from new class comma f, where image f is converted to the class specified in parameter new class and output it as g. Next is function used for image scaling. Function gscale is used for this purpose, having general syntax as g equals to gscale f comma method comma low comma high, where f is the image to be scaled. Next is histogram processing and function plotting. Intensity transformation functions based on information extracted from image intensity histograms play a central role in image processing in areas such as enhancement, compression, segmentation, and description. So, generating and plotting image histograms. The core function in the toolbox for dealing with image histograms is iamhist, whose basic syntax is shown as h equals to iamhist f comma b, where f is the input image, h is its histogram, and b is the number of bins used in forming the histogram. If b is not included in the argument, b equals to 256 is used by default. A bin is simply a subdivision of the intensity scale. Histograms can be plotted by using bar graph also. For this purpose, the following function can be used as bar and in parentheses write HORZ, Z, width, where Z is a row vector containing the points to be plotted. HORZ is a vector of the same dimension as Z that contains the increments of the horizontal scale, and width is number between 0 and 1. Stem graph is similar to a bar graph, whose syntax is shown here as stem and in parentheses include HORZ, Z, color line style marker, fill, where Z is a row vector containing the points to be plotted and HORZ is as described for function bar. If HORZ is omitted, the horizontal axis is divided in units from 0 to length Z as before. The argument color line style marker is a triplet of values. Histograms are also plotted using plot command, having syntax plot and in parentheses include HORZ, Z, color line style marker. Next is histogram equalization. Histogram equalization is implemented in the toolbox by function histeq, whose basic syntax is shown as h equals to histeq and in parentheses include f comma nlev, where f is the input image and nlev is the number of intensity levels specified for the output image. If nlev is equal to the total number of possible levels in the input image, then histeq implements the transformation function directly. If nlev is less than total number of possible levels in the input image, then histeq attempts to distribute the levels so that they will approximate a flat histogram. So next is histogram matching. Histogram equalization produces a transformation function that is adaptive in the sense that it is based on the histogram of a given image. However, once the transformation function for an image has been computed, it does not change unless the histogram of the image changes. As denoted in the previous section, histogram equalization achieves enhancement by spreading the levels of the input image over a wider range of the intensity scale. So this is discussed in this lecture, that This does not always lead to a successful result. In particular, it is useful in some applications to be able to specify the shape of the histogram that you wish the processed image to have. The method used to generate an image that has a specified histogram is called histogram matching or histogram specification. The toolbox implements histogram matching using the following syntax in histeq, as G equals to histeq f comma hspec, where f is the input image, hspec is the specified histogram, and G is the output image whose histogram approximates the specified histogram hspec. This vector should contain integer counts corresponding to equally spaced bins. A property of histeq is that the histogram of G generally better matches hspec with length hspec is much smaller than the number of intensity levels in F. So this is all in this lecture. In our next lecture, we will discuss about spatial filtering. Thanks.